record here. Okay, so you can show and we'll see this in the classical probability model. That the probability of any event equals the number of items in that event divided by the number of items in the sample space. Now, how does that come about? Well, it comes about because the probability of E simple, they're all the same, right? The probability of the probabilities of simple events are the same. That is, all outcomes are equally likely. All individual outcomes are like correspond to the simple events. All outcomes are equally likely. So it's a special case. Okay, and the thing is, the idea is here is the probability of a union, if A and B are simple, then the probability of the union of A and B, because their intersection, is zero because they're simple events. They each have a different one, is going to equal the probability of A plus the probability of B. We have to have this union thing that it's dependent on this. So these are equal, right? So that corresponds to the fact that if these are simple, the number of elements in this is going to equal 2. So in general, we need to have that the probability of the union of two non-intersecting events adds up. And when you do that, you get this formula. So this sort of tells you that this formula corresponds to the classical model. Well, here we have, as numbers, we have one here, and the sample space is 4. So the probability of this event is 1/4. The probability of the outcome with 2 is also going to be 1/4, like that. Okay, so that's where this is coming from. Now, I want you let's go on to item D. Consider the event in which the outcome is 3 or less. How is this event defined? So again, write down, see yourself if you can write down how is the event that the outcome is 3 or less defined. And okay, we have one person has an idea. 2 people have an idea. Okay, 3 people have an idea. Okay, so at least some people have not. Well, so you probably wrote down this. Hopefully you wrote down this. The event was 1, 2, 3. That's the event that 3 or less. So we can add, that's an event, right? It's a subset of the sample space here, 3 out of the 4. So what's the probability of this event event? How is the probability of this event defined, and what is that probability? So it's defined via the formula for classical model as the number of events, number of items in the event, number of outcomes in the event, number of elements in the set divided by the set. Well, this is going to be 3/4. So the probability of this is 3/4. You can see that the probability that it is greater than 3, which is just going to be the 4, that is the probability of the event E greater than 3 is going to equal 1/4, because there's only going to be one event here, the 4. And the 3/4 plus 1/4 is 1, which occurs. Okay. Now, let's look at F. Consider the event E-any in which the outcome is either 1, 2, 3, or 4. How is this event defined? Okay, we have one, maybe two people, or maybe one carried over from last time. Anyone else? Okay, we have 3 people. Well, that's a fair amount. Okay, so what you do is you put the curly brace for the set, 1, 2, 3, 4, and that's going to equal the sample space, right? Because it's all and then what's the probability of this event? Well, it's the number of items in the event divided by the sample space size. Jumping the gun there a little bit. Okay, so the number of outcomes in this event is 4. The number of outcomes in the sample space is 4, so it's 4/4, which equals 1, which means that it's absolutely certain if in the probability experiment you roll the dice 1, 2, that it has a
Professor?
4-sided dice, you get 1, 2, 3, or 4. Dipanshu, yes, question.
Yeah, I had a question, but why did you write a 5 in front of 1, 2, 3, 4?
Oh, I didn't mean to write a 5. It's my script is this is S. I meant to write an S, not my S looks like a 5, right? This is not a 5. Yeah, unfortunately, the 5 sort of looks like an S, and I was writing it looked like a 5, which you're right that if I had written 5 there, that would have made no sense at all because a set's not a number. Okay. Well, there is the beginnings. Now let's go on. Here's a more complicated experiment so we can practice what we've done, do the same things with a different experiment. So consider the experiment of tossing 2 4-sided dice. Say one's green and one's red, right? Just to distinguish them so we can know. So what's the size of the sample space? Well, each outcome consists of the experiment is you roll the 2 dice. So there's going to be a number up on the green dice and a number up on the red dice. So an outcome consists of a result for the green die and a result for the red die. So it's going to be sort of a green 1, 2, 3, or 4 and a red 1, 2, 3, or 4. So we need a notation to write down so we can talk about these outcomes. Let's write the green die result first, right? And list all the possible outcomes, right? For each outcome, and list all the possible outcomes. The green die face-up number can be 1, 2, 3, or 4. The red die face-up number can also be 1, 2, 3, or 4. So here's our notation for the outcome in which the green is 4 and the red is 3. We're just going to, so you don't read this as 43. This is green 4, red 3, or just 4, 3. So read the numerals individually. It's not the number 43. It's the outcome 4-3. Okay, so let's find the size of the sample space. Well, I have 2 slots here. Let's see, how can I make any outcome? Well, there's 4 choices for the red dice and 4 choices for the green dice. So they're independent choices. So in our counting, we'd have 4 times 4 equals 16. So this sample space is 16. Now, B, well, if I sort of did that for you. B, what is, I'll let you work on this one, or give you time to work on this one. So what is the notation for the outcome of a green 4, a green 2, and a red 4? The outcome for, what's our notation for a green 2 and a red 4? Okay, anyone else? We have one person. Anyone else going to raise their hand? Okay, you've got 2 people, maybe some more. Okay, we probably have about 3 people. Okay, well, what you just write here is you just write 2, 4, not 24, 2, 4. Okay, what's the definition of the event in which just this outcome occurs? What should I write here? Anyone have any ideas? I'll let you answer if you want. What should I write here for the event in which just this outcome occurs? Dipanshu, what do you think? What should I write here?
Maybe 2, 4, and curly braces.
Yeah, so you have curly braces because it's an event's a set, and you write 2, 4 like that. That's it. And this connotes one element. So if I had an event with 2 elements, it would be 2, 4, comma, something, comma, something. Okay. So what's the definition of the event in which the green die produces a 3? This is a little bit trickier.
Can I give a try on this?
Excuse me?
Can I give a try on this?
Yeah, sure. Tell
So
me.
is it
Okay, go
3,
ahead.
1, 3, 1, 3, 2, 3, 3, 3, 4?
This is what you mean.
Yep.
And that is correct because it's the green is a 3, but the red can be anything, right? So that's correct. And let's see. So here's sort of a picture of the sample space in which we're drawing a picture of the sample space in which the rows are green and the columns are red. So we're going now. Unfortunately, I think it would actually be I've put 1, 1 here, and this is the event green 1, red 1. This is the event green 3, red 4. So what we just did up here, these ones here would be in here. 3, 1, 3, 2, 3, 3, 3, 4. So this is going to be um, green 2, 1. So it's going to be 2, 2, 2, 3, 2, 4. This will be 1, 2, 1, 3, 1, 4, and 4, 1, 4, 2, 4, 3, 4, 4. Okay. So so this is going to help us sort of choose certain, if you draw this picture of sample space, yeah, we have all 16 outcomes, right? Well, we've actually drawn each sort of block here looks like one of the simple events, right? That would just include one of those, like the event up here, 2, 4 would just be this one here. Okay, now consider the event consisting of 2 outcomes, a green 4 and a red 3, or a green 3 and a red 4. How is this event defined? Well, as you can yes, it should be 4, 3, 3, 4. And you can see up here, it's going to be these two elements there that would be in this set. Now, according to the classical probability model, in which each simple outcome has an equal chance of occurring, this means the probability of event E will be this ratio. What's the probability assigned to E 3 and 4? This is that the green is 3 and the red is 4. What fraction should I write here? So write that fraction down or fix it. And if you, okay, we have one person that has an answer. Does anyone else want to claim an answer? Okay, we have 2 people having responded, 3 people. How about one more? Do you think one more person could rise to the occasion? Oh, we lost one. Okay, well, I assume that 3 of you put down 1 over 16, right? Is that what you guys did? Well, tell me if you didn't, if you want to.
No, why isn't it 1:8?
Excuse me?
Why isn't it 1:8? It
Oh,
should be 2
because,
to 16.
okay, so, and I think you're right. The point is, this is 3 and 4, right? This is a 3, this is either one, so there's 2 events here. So it should be 2 over 16, which equals 1/8. You're absolutely right. What I was thinking of is the probability of E 3, 4, which would be 1/16. But then E43 would be 1/16, and 1/16 plus 1/16 is 1/8. So you're absolutely correct. That would be the right answer. Okay. Uh, mm, I think this is another way of saying, I think there's a bug here in the sense that this is another way of saying the same thing. E43 any color is going to be 4, 3, 3, 4. So the probability. But then what about this one? What's the probability assigned to E12? What number should I put here?
1, 2.
Uh, what the
In a
probability?
basis. Oh, probability. So 1:16.
Yeah, 1/16. Because this is because the event E12 is just the subset with just the outcome 1, 2. That is a green 1 and a red 2. Okay, here is this. I've drawn the same event, but I drew a different picture. I have the 1, 1 up here, and this because anyway, for whatever reason, consider the event consisting of the sum of the 2 dice yielding 5. This is the point of this diagram. So, what's the event of the sum where they sum to 5? Well, one thing you can do is you could just circle the elements on this square that where they sum to 5, and it's easy to see which ones they are. So Dipanshu,
1, 4, 2, 3, 3, 2, 4, 1.
Yeah, so you can see I just circle these, right? Because this row here, these are the ones that add to 6, to 7, to 8, to 4, to 3, to 1, because it's going up, this is 2, 3, 4, 5. So you're going to write up here for the event 1, 4, 2, 3, 3, 2, 4, 1. And the probability of this event is
1:4.
yeah, because it's going to be 4, the number of this over 16. When you reduce that to fractions, it's going to be 1/4. There's two ways to quote this. Either this way is a better understanding of what the fraction is. This way of writing it, although it's not a reduced fraction because you have a 4 in the numerator and denominator, it is a factor of the numerator and denominator. It sort of illustrates where it came from in terms of the formula. The probability is the number of outcomes in the event divided by the number of outcomes in sample space. Okay, so let's see. I think there's more here, but I think I should let you guys work on these sort of so you can use that as practice so far. Then let's look at the other probability programs. Oh, we have dice. And this, you roll a dice a certain number of times, and then what we're doing is the probability of the sum. It is the one we just did, the probability of a sum, but it's dealing with a 6-sided dice. So we have the totals here, you see, of two dice is 1 plus 1 is, so these are the probabilities of the totals we have, because you have the sum here. And so we have the, so for example, if the sum is 1 plus 1 is 2, then it's going to be in slot 2 minus 2. It's going to be this first slot here. So this is what we're going to get is a little bar chart, a little sort of count of the, if I roll 2 dice, what's the probability of the sum? Okay, so let's run this and see what happens. We can do, let's say we do just 10 rolls. Okay, so you can see here that there were, it's just a scattered amount, and there's not necessarily obviously any pattern here. And let's try it again, but say with 100 rolls. And you can see then it's like this, the numbers at the ends are relatively small, and they're beginning to stack up in the middle, because it turns out there's many more ways to get a number in the middle, right? And you can see here like 8 is 20%, 15%. So let's see what, because these are statistics, right? This is the statistics of what happened. There's 1,000, okay? And now it looks like, well, 6 is large. 6 is the largest, and then these are all close to 15%. Let's do it again with 10,000, and we end up with 7 being 0.16, 0.14, 0.14, down to 2.6. We do it again, say with, that was 10,000. Now we want 100,000. Okay, you can see up here the numbers are getting to be in the thousands for each one of these. But then you notice the difference between here. This was for 7, it was 163. For 7, it's 165. Up here, it was 14, 138, 254, 28. So it's beginning to show a pattern, right? Where it turns out that, and it's going to turn out that 7 is the most, if you roll 2 dice, the most likely sum of the 2 dice is going to be 7. Okay, well, I have some more programs here. Oh, let's open the second one here. And this second one, I think, let's see how many rolls. Let's do 10,000. Okay, what it does is it makes a bar chart, which is much easier to see the sort of what's going on. The sum showing, this shows the with 10,000 rolls, it shows how many rolls were in each one. And you can see it peaked around the 7. And here's this. Now let's then try it again here with 100,000. And there it's beginning to sort of it's still 7, but it's beginning to coalesce to certain values. And let's do then we have, that was 100,000. Here's let me say this is 1,000,000. Okay, now it's beginning to settle down to particular percentages and probabilities. And it turns out that we can, so the issue is, how can we predict? We would like to be able to predict the probability of the sum for for a 6-sided dice. So that's one little project, is to understand where this is, um, what's happening. Dipanshu, you have a
Yeah,
question
I had
or?
a question, Professor.
Oh, let me just a second. Okay, go ahead.
Can I ask the question?
Yes, go ahead.
Why do you want to predict the probability?
Oh, well, because that's what a probability is. It's a prediction. This is statistics. This is showing you what happened.
But the probability is a prediction. I get it, but how can you just predict that this is gonna happen this time? Let's suppose if
Well,
I
the
flip a
question is,
coin, if I flip a coin, I mean, it doesn't has to be 50-50.
right.
It could
But the
all.
question is, what you want to do is you want to know, see, the probability tells you what's most likely. Now, and you ask, well, what's most likely is if I run it for, if I do it many times, I'm going to get a certain frequency of results that mirrors that likelihood. So if you were to roll 2 dice and you wanted to choose the most likely sum, you would more be most likely to be correct if you chose 7 than any other number. Right? So that's all, because the probability is just a fraction. It's just telling you that if all things were equally likely, there's more ways for it to be a 7 than it is to be something else. So if I look at when I looked at this, right? Not this one, the other one. Let's see. This one here. Okay, we did this square in the exercise, right? Where we had new page after, where we had a square, right? Where we had 1, 1, and down here we had 6, 6, and over here we would have 1, 6, and 6, 1, right? And you can ask, well, because if you want, like, there's going to be like 1, 2 here and 2, 1 like this. And so down this diagonal, you can see in this box, if I was to draw it for the outcomes, you can see how many, for 6-sided dice, what's the sample space size? Well, it's going to be 6 times 6, which equals 36, right? So how many events are there? You can see here on this long diagonal, I have 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, and 6, 1. I have 1, 2, 3, 4, 5, 6. So the event that I get sum to 7 has 6 events. 1, 2, 3, 4, 5, 6, right? So the probability that you get sum to 7 is going to equal 6 over 36, which equals 1/6. Now, what just to connect up with the numbers in that, that's 1.66, right? And we could do it in Python too. But over, let me see, let's just, uh, well, you notice here that it's that the um, number here is is almost 0.66, right? Because we did it a million times. So if we took, oh, I have to can't if I do, let's do this. Uh, so if I have here 166,962, and I divide that by a million, right? I'm going to get 0.167. So I'm beginning to get the expansion. I'm beginning to pick up this number of 1/6. So what's going on? So I can predict these this pattern of as I get larger and larger numbers of rolls. This number here is going to get to be like, if I do 10 million, it's going to get closer and closer to 1,666. So this is like 1/6, and I can look at this square here and predict all these numbers, right? So it's probably the least accurate of this one, but then it gets more accurate. So I can layer it and see, I can write away from this square, or just, writing down, seeing that the long diagonal of this square was the ones that add to 7, and they're the ones that are going to be the most, um, the most number of outcomes in the event. So it gives a way to understand the statistics and predict it. Is that, I'm not sure if that answers your question or avoids it, but what do you think? So it's uncertain, but there's a pattern. Now the pattern appears in the statistics only when we do it for many, many times, like a million times. So any given choice, any given, like if you just had like one toss of the dice, you could say, well, the probability is going to be 1/6. It's a 7, and it's going to be 1/30. The probability of the event 1/1 that it sums to a 2, right, is just going to be 1/36. Meaning that there's only 1 out of 36 possible ways. The 1/6 is telling you that there's 6 ways out of the 36, and they're equally likely. So you're going to have the highest probability when you have the most number of events. Okay, that's all that's going on with this. It's just a way of getting some kind of pattern and understanding the what's going on when you have patterns of uncertainty. Uh, okay, Julian, I'm sorry I didn't see your comment. I'm not sure, but anyway, hopefully that was resolved. Okay, so let's go on to see if we've missed anything in the chapter. So we have the Python. It describes these experiments. So you should try them out yourself. We have probability experiments. Yes, we covered that. Outcomes, sample space, events, and simple events. Okay. And I think, oh, we didn't do mutually exclusive events. Two events that have no outcome in common and so can never occur at the same time are called mutually exclusive events. That's what, if they're mutually exclusive, um, their intersection is the empty set and the probability of the empty set is zero. So that means the probability of two mutually exclusive events occurring is zero. There's some exercises there in the text. Probability models. Okay, here's an example. The probability of an event is a number between 0 and 1. Okay, here's a requirement. But the probability of a simple event equals the probability associated with a single outcome. The assignment must be made so the sum of the probability of simple events equals 1. This is, we talked about earlier, that this has to be the case. And there's some extra, these are the ones we talked about, and I mentioned this fourth one. The probability of any union of mutually exclusive subsets equals the sum of the probabilities of each of those subsets. So that if you union together two subsets or two events and there's no outcomes in common, then the probabilities have to add. And that way you can build up every subset out of elementary sets, which leads to the final this classical probability model when you choose them all to be equal. And here's the statement of this, some examples and exercises you should go through. Now, this is basically what we need to do for this week, so to speak. Let's see, let's go to the new exercises that appear for probability. All deal with like sample space, outcomes, events, right? And probability, giving you some examples. And kinds of events, mutually exclusive events or independent events. And independent events, I think we've done mutually exclusive ones, we haven't done independent ones, because they're mutually exclusive events, there's a connection between the two events. They prevent, in other words, if one occurs, the other can't occur, okay? But there's other connections between events, right? And it turns out that this connections between events are where a lot of the puzzles come from. The probability puzzles, and let me have to deal with, oh, not this one, but let's deal with the other one. Okay. So we have here the idea of, let me see, this was topic 5. So this is like topic 6 is connections between events. And so the one connection is mutually exclusive events. And that just means that if event 1, mutually exclusive events are ones for which their intersection, because they're both subsets, is the empty set. So the probability of E1, E2 of mutually exclusive events is going to equal the probability of E1 plus the probability of E2. And we can see that's consistent with the classical probability model, because the number of outcomes in the union is going to equal the number in E1 plus the number in E2 minus the number in the intersection, right? Well, the intersection here, if this is the empty set, then this is 0. So then you have this counting. So the probability of E1 union E2 equals the number in E1 union E2 over the sample space size, which equals E1 over S plus E2 over S, because this goes in there, and then that's going to equal the probability of E1 plus the probability of the other mutually exclusive event. So we get, if you have mutually exclusive events, we had an addition rule for in counting, and that mutually exclusive counting rule goes over to this case. And so now the question is, what do we mean by independent sets? Well, that's a little bit, that requires us to talk about something called conditional probability, which is the topic next week, because that's a larger topic. And that's also where we define independent events. Okay, but we can start with I think I've been recording for too